Hello, my name is Kevin Craig. I have created 12 modules that cover electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. What is mechatronics? The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is now used around the world to represent the multidisciplinary field we know as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This module is Module 3 on capacitors. The topics I will cover include an introduction, types of capacitors, charging and discharging a capacitor, energy stored in a capacitor, capacitors in AC circuits, capacitive reactance, capacitors in series and parallel, and a capacitive voltage divider. Here you see pictures of the wide assortment of capacitors available. An introduction. A capacitor is a passive device that can store energy in an electrostatic field formed by electrical charges producing a potential difference across its plates when connected to a voltage source. It consists of two or more parallel conductive metal plates separated either by air or an insulating layer called a dielectric, such as wax paper, mica, ceramic, plastic, or liquid gel, as used in electrolytic capacitors. When a DC voltage is placed across a capacitor, positive charge accumulates on one plate, as we see here, while negative charge accumulates on the other plate, as we see. The plates remain charge neutral, and a potential difference is established between the plates. You see the conductive parallel plates, the dielectric, the electrostatic field when we apply a DC voltage. When used in a direct current or DC circuit, the capacitor charges up to its supply voltage, but blocks the flow of current through it because the dielectric of a capacitor is non-conductive and basically an insulator. When a capacitor is connected to an alternating current or AC circuit, the flow of the current appears to pass straight through the capacitor with little or no resistance. This does not happen. More on this later. The flow of electrons onto the plates is called charging current, which continues to flow until the voltage across the plates is equal to the applied voltage. The strength or rate of this charging current is at its maximum value when the plates are fully discharged, the initial condition, and slowly reduces in value to zero as the plates charge up to a potential difference across the capacitor plates equal to the source voltage. When charging a capacitor, we see on the plot of charge versus time, and the slope at any point along this curve is current. we see that the maximum slope occurs at time t equals 0. The current is maximum there, and then eventually becomes 0 when the capacitor is fully charged. At time t equals 0, the rate of change of the voltage across the capacitor, the potential difference, is maximum at time t equals 0 and reaches a value of 0 when the potential difference is at a maximum and the capacitor is fully charged. The amount of potential difference present across the capacitor depends upon how much charge was deposited onto the plates by the work being done by the source voltage and by how much capacitance the capacitor has. The property of a capacitor to store charge on its plates in the form of an electrostatic field is called the capacitance, C, of the capacitor. Capacitance C is also the property of a capacitor which resists the change of voltage across it. In a parallel plate capacitor, the larger the plates, more area to store charge, and the smaller the separation, the negative charged plate has a greater effect on the positive charged plate. The greater will be the charge that the capacitor holds for any given voltage across its plates. Capacitance C equals charge Q over voltage V. And the unit of capacitance is farad, F. 1 farad equals 1 coulomb per volt. Capacitance C is always positive. A farad, named after Michael Faraday, is a large unit of measurement. So microfarad, 10 to the minus 6th, is used, designated as a microfarad, or a nanofarad, 10 to the minus 9th, is used, designated as a nanofarad. C, the capacitance of a parallel plate capacitor, is proportional to the surface area A in meters squared. Here we see the surface area of the plates in meters squared, surface area in meters squared. Inversely proportional to the separation distance D in meters. Here's the separation distance D in meters, and we see it here also on this diagram. Capacitance C equals the permittivity, epsilon, times the area divided by D, the distance, where epsilon represents the absolute permittivity of the dielectric material. The permittivity of a vacuum and approximately air, epsilon 0, is 8.84 times 10 to the minus 12th farads per meter, or 8.84 picofarads per meter. A picofarad is 10 to the minus 12th farads. The various insulating materials used as the dielectric in a capacitor differ in their ability to block or pass an electrical charge. The dielectric material can be made from several insulating materials or combinations of these materials, with the most common types used being air, paper, polyester, polypropylene, mylar, ceramic, glass, oil, or a variety of other materials. The factor by which the dielectric material, or insulator, increases the capacitance of the capacitor compared to air is known as the dielectric constant, small k. And a dielectric material with a high dielectric constant is a better insulator than a dielectric material with a lower dielectric constant. The dielectric constant K is also known as the relative permittivity, epsilon sub r. So K equals epsilon sub r, which is the permittivity divided by the permittivity of a vacuum. Values for the permittivity, the relative permittivity, for common insulators are paper between 2.5 and 3.5, glass between 3 and 10, mica 5 to 7, wood 3 to 8, metal oxide powders 6 to 20. So the capacitance equals the permittivity of a vacuum times the relative permittivity times the area of the plates divided by the distance between the plates. All capacitors have a maximum voltage rating. WV equals working voltage. And when selecting a capacitor, consideration must be given to the amount of voltage to be applied across the capacitor. If the voltage applied across the capacitor becomes too great, the dielectric will break down, known as electrical breakdown. And arcing will occur between the capacitor plates, resulting in a short circuit. The working voltage of the capacitor depends on the type of dielectric material being used and its thickness. In practice, a capacitor should be selected so that its working voltage, either DC or AC, should be at least 50% greater than the highest effective voltage to be applied to it. Another factor which affects the operation of a capacitor is dielectric leakage. Dielectric leakage occurs in a capacitor as the result of an unwanted leakage current which flows through the dielectric material. Modern capacitors can be classified according to the characteristics and properties of their insulating dielectric. Low loss, high stability, such as mica, low K ceramic, polystyrene. Medium loss, medium stability, such as paper, plastic film, high K ceramic. And polarized capacitors, such as electrolytic and tantalum. The dielectric provides the following advantages. The dielectric constant is the property of the dielectric material and varies from one material to another, increasing the capacitance by a factor of K. The dielectric provides mechanical support between the two plates, allowing the plates to be closer together without touching. Lastly, the dielectric increases the maximum operating voltage compared to air. Capacitors can be used in many different applications and circuits. Capacitors are used to block DC current while passing time-varying waveforms. This ability to block DC current enables capacitors to be used to smooth the output voltages of power supplies, to remove unwanted spikes from signals that would otherwise tend to cause damage or false triggering of semiconductors or digital components. Capacitors can also be used to adjust the frequency response of a circuit or to couple together separate circuit stages that must be protected from the transmission of DC current. At DC, a capacitor has infinite impedance. It's an open circuit. At very high frequencies, a capacitor has zero impedance. It's a short circuit. Types of capacitors. The types of capacitors available range from small, delicate trimming capacitors to large power capacitors. The different types of capacitors are usually distinguished by the dielectric material used. Film capacitors are most common, ranging from 5 picofarads to 100 microfarads, with the difference being in their dielectric properties. Polystyrene, polycarbonate, or Teflon film dielectric capacitors are called plastic capacitors and operate well at high temperatures, have small tolerances, and are highly reliable. Examples are shown. Here is a rectangular metallized film capacitor. Here is a cylindrical film and foil capacitor. Ceramic capacitors, called disc capacitors, have a high dielectric constant and small physical size. They are non-polarized with values ranging from approximately 1 picofarad to 1 microfarad. The 154 on this ceramic capacitor means 15 with 4 zeros in picofarads. So 150,000 picofarads, which equals 150 nanofarads, or 0.15 microfarads. Here we see pictures of electrolytic capacitors. These are used when capacitance values are required. High capacitance values are required. They are polarized with clear markings, plus and minus. They must not be used in AC applications. They come in 2 basic forms, aluminum and tantalum. The aluminum electrolytic capacitor, shown here, comes in 2 types, plain foil and etched foil. They have high breakdown voltage along with high capacitance values for their size. Tantalum electrolytic capacitors have better dielectric properties than aluminum, resulting in lower leakage currents and better stability. Here I see a picture of the charging of a capacitor. When the switch is set to A, the capacitor will charge. And then if the switch is set to B, the capacitor will discharge, turning on the lamp, and again losing its energy through heat and light. A real capacitor will slowly discharge itself over a long period of time due to the internal leakage currents flowing through the dielectric. Energy stored in a capacitor. The pure and ideal capacitor, pure only has the attribute for which it is named, capacitance, no parasitic resistance or inductance, and ideal, which means linear. The pure and ideal capacitor stores in its electric field all of the electrical energy supplied to it during the charging process and will give up all this energy if completely discharged, say by connecting it to a resistor. The work done to transfer a differential charge, dq, which is just a small amount of charge, through a potential difference V is just the product of V and dq. The total energy stored by a charged capacitor is the integral between 0 and Q of V dq. If I substitute in for V using the definition of capacitance, I get this expression. Performing that integration, I see that the energy stored by a charged capacitor is 1/2 Q squared over C, or more commonly seen as 1/2 C B squared, where V is the voltage across the capacitor. Capacitance is charge per volt. And this is true irrespective of how the final voltage or charge was built up. There is no current through a capacitor. An equal amount of charge is taken from one plate and supplied to the other by way of the circuit external to the capacitor. Capacitors in AC, alternating current circuits, and capacitive reactance. When a capacitor is connected across a direct current supply voltage, it becomes charged to the value of the applied voltage. A charging current flows into the capacitor, opposing any changes to the voltage at a rate that is equal to the rate of change of the electrical charge on the plates until the capacitor is saturated. The definition of capacitance is charge equals capacitance times the voltage across the capacitor. If I take the time derivative of both sides of this equation, dq dt, which is the current flowing through the capacitor, or really in the circuitry surrounding the capacitor, equals the capacitance times the time rate of change of the voltage across the capacitor. So if we apply an alternating current, AC, the capacitor will alternately charge and discharge at a rate determined by the frequency of the supply. Then the capacitance varies with frequency as the capacitor is being constantly charged and discharged. We know that the flow of electrons onto the plates of a capacitor is directly proportional to the rate of change of the voltage across those plates. Then we can see that capacitors in AC circuits like to pass current when the voltage across its plates is constantly changing with respect to time, such as in AC signals, but it does not like to pass current when the applied voltage is of a constant value, such as in DC signals. In the purely capacitive circuit, the capacitor is connected directly across the AC supply voltage. As the supply voltage increases and decreases, the capacitor charges and discharges with respect to this change. We know that the charging current is directly proportional to the rate of change of the voltage across the plates, with this rate of change at its greatest as the supply voltage crosses over from its positive half cycle to its negative half cycle, or vice versa at points 0 degrees and 180 degrees along the sine wave. Current flowing through the capacitance in AC circuits is in opposition to the rate of change of the applied voltage. Like resistors, capacitors also offer some form of resistance against the flow of current through the circuit. This is called reactance or impedance. Here we see a plot of voltage and current versus angle theta of the sine wave from 0 to 360 degrees. Omega, which is the frequency of the sine wave in radians per second, times time gives me angle in radians. 360 degrees is 2 pi radians. And we see that as the voltage changes, the capacitor charges, then discharges, charges, and then discharges. And we see that the voltage lags the current by 90 degrees. The mathematics of the situation are as follows. The definition of capacitance is that charge equals capacitance times the voltage across the capacitor. If I take the derivative of both sides of the equation, dq dt, the rate of change of charge, is current through the capacitor, or in the circuitry around the capacitor. And this equals capacitance times the time rate of change of the voltage across the capacitor. Now, we don't work with derivatives or integrals or differential equations or differential constitutive equations because we transform all of those using the differential operator into algebra. So this can be written as the current through the capacitor equals C times the differential operator applied to the voltage across the capacitor. The impedance of the capacitor, which is the voltage across the capacitor, divided by the current through the capacitor, by algebra, is 1 over CD. It's all algebraic. If I let D equal J, the imaginary number, square root of -1, times omega, the frequency in radians per second, I get the expression for the impedance of the capacitor as a function of frequency, 1 over C J omega. This is the impedance of the capacitor, Z sub C, or reactance, X sub C. The magnitude of this impedance, which is the same as the magnitude of this reactance, is 1 over C omega. And omega is 2 pi times F, frequency in hertz, times the capacitance. The angle, the phase angle of this capacitance element is -90 degrees. So if I plot reactance magnitude in ohms from 0 to infinity, and frequency 0 to a large number in hertz, I see that as the frequency increases, the magnitude goes from a very large number to a very, very small number. The plot is one of 1 over 2 pi fc. The ability of a capacitor to oppose or react against current flow by storing charge on its plates is called reactance. And like resistance, reactance is also measured in ohms. Capacitors in series and parallel. First, capacitors in parallel. Here we see 3 capacitors in parallel. They have the same voltage across them. Capacitors in parallel have the same voltage across them. The total capacitance of capacitors connected in parallel is the sum of the individual capacitances. Capacitance is proportional to the area of the conducting plates. Placing capacitors in parallel is like increasing the area of the capacitor plates. So this is opposite to the way resistors in parallel are combined. Capacitors in series. Capacitors in series, and we see 3 in series here, have the same current through them. The total capacitance of capacitors connected in series is the reciprocal of the sum of the reciprocals of the individual capacitors. Capacitance is inversely proportional to the spacing between the conducting plates. Placing capacitors in series is like increasing the separation between the capacitor plates. So capacitors in series is analogous to resistors in parallel in terms of the formula we use to find the equivalent capacitance. On the breadboard, I have 2 capacitors in series. And when I measure the equivalent capacitance, I get the value shown. If I measure the capacitors individually and use the formula for capacitors in series, the formula predicts a value comparable to what I measure for the effective capacitance. Here you see two capacitors in parallel. If I measure the effective capacitance, I get the value shown. If I use the formula for two capacitors in parallel, substitute in the values for the individual capacitances, I get the value shown, and it's comparable. A capacitive voltage divider is similar to a resistive voltage divider. In fact, a voltage divider can be created using any impedances. Here I use two capacitors whose impedance is given by 1 over C times S. But what is S? S is just another form of representing the differential operator. When we see S, we should think differential operator. The reason I use that here is because when we use MATLAB and Simulink, S is what is recognized there, not capital D for the differential operator. Since we do everything in algebra, we need to get used to using S in place of D, especially when we use MATLAB and Simulink with our analysis. So knowing what my formula is for my voltage divider, I can see that the voltage here at the node V is equal to Vin times the voltage divider ratio, Z2 over Z1 plus Z2. And if I just substitute in the values for those impedances and do the math, the algebra, I get the final relationship is that V at the node between the two capacitors is equal to Vn times C2 over C1 plus C2. And this is a capacitive voltage divider. This completes our module on capacitors. Thank you for your attention.